Lisa, please start sharing your screen. And this is work done between or with David Hathaway. Lisa and David have been working on this for a while. Pattern tracking of SDO data, what we've learned about the axisymmetric flows in solar cycle 24. Lisa, please.
Thanks so much, Mark. I want to start by thanking the organizers for inviting me to talk to all of you today. Today I'm going to talk about work that David and I have been doing pretty much since the beginning of HMI. The axisymmetric flows, differential rotation, meridional circulation are essential components of the solar dynamo. So at about the start of HMI, David and I had just begun to do magnetic pattern tracking on MDI data to characterize these flows. I want to emphasize that we're doing pattern tracking and not feature tracking. These are different. I'm not going to go into detail here, but these are different. We also measured these flows at that time. We also measured these flows during the approximate 1 year of overlap between the MDI and HMI data. And we thought we were long overdue to give you an update. So in the meantime, we have improved the magnetic pattern tracking code. Since then, we've made several improvements based on a recent study by Mahajan et al. It's in press now. In particular, the improvements include correcting some peak locking errors that are inherent to measuring sub-pixel shifts in the pattern motion. We also used a broader search area for finding the correlation peak. And this allows for better sampling of the Gaussian distribution of the flow values. We removed a systematic shift away from disk center. This shift is independent of time lags, and it's analogous to the same shift that has been seen in helioseismology. We can quantify and remove this shift by comparing tracking results using the different time lags. And here I'm showing the shift in the meridional circulation and how it varies with the different time lags. And we find that overall, with any time lag that you use, you get a shift of about 200 kilometers per shift. And so we remove that. And now we have completed this analysis. We have maps of the near surface flows over the entirety of solar cycle 23 and 24. We repeated the analysis on all of the MDI data and the HMI data. So we have 2 full cycles here. We're currently working on writing up this paper, and we do plan to make these flow measurements available on our website, solarcyclescience.com. Today I've got a lot of material to cover, but I do want to highlight some of the preliminary results from these 2 cycles of measurements. Let's get started with the torsional oscillations, and this really reflects a lot of what you heard from June Wei earlier with the results reported by Rachel Howe and others. And most importantly, we see that the torsional oscillation signal includes this high latitude spin up near solar cycle maximum. This corresponds to an increase in the angular momentum of the near surface shear layers. And we find that the high latitude spin up was much more pronounced in cycle 23 than it was in solar cycle 24. We also see that there's an equatorial spin up that was less pronounced in solar cycle 23 than it was in solar cycle 24. We can also plot the, if we fit these flow profiles to Legendre polynomials, we can plot individual coefficients to reveal specific features of the flow profiles. In particular, the T1, we find this represents the solid body rotation, and thus the variation in the angular momentum, and we see that it does have a solar cycle dependence. The T3 coefficient represents the shear in the differential rotation, and we see that it was much stronger, i.e. more negative in solar cycle 24 than it was in solar cycle 23. The T5 coefficient, which is essentially reflective of the differential rotation in the active latitudes, we find that it was much stronger, more negative in solar cycle 24 than in solar cycle 23. If we take a look at the meridional circulation, we do find that there's the slowdown of the meridional flow in the active latitudes. We see this both in cycle 23 and 24, but this was much more pronounced in cycle 23 than in solar cycle 24, which is understandable given that solar cycle 24 was considerably weaker than solar cycle 23. We also note that there is This effect was offset by about 2 years, and this is due to, in solar cycle 24, and this is due to the hemispheric asymmetry in the timing of the active region emergence in solar cycle 24. In the meridional flow, we also find evidence of transient countercells at the high latitudes. We were very surprised to see what appears to be countercells in both the north and south hemisphere in the last few years. We did see it in our HMI measurements for solar cycle 23, but they had such an odd behavior. They began in one hemisphere, and it's almost as if they shut off here and turned on here. And we were concerned that this might have been an instrumental artifact, and so we weren't sure if we could really believe it. But now that we're seeing these countercells reappear in solar cycle 24 now, I think we need to take another look at this. This was very surprising, and I think this really emphasizes the fact that we really need to get to the poles and get better measurements of these high latitude flows. I just want to emphasize that the meridional flow is very, very weak, and so it's really difficult to measure from the ecliptic. So we really do need a polar mission to be able to accurately measure these flows. We can also take a look at the Legendre coefficients if we fit for the meridional flow. The second coefficient represents a single cell in each hemisphere. Well, we find that it weakened strongly at the start of cycle 23, but not so much in 24. The third coefficient, which represents north-south asymmetry, changed sign over solar cycle 23 as the countercell switched hemispheres. And the fourth coefficient, which represents 2 cells in each hemisphere, we see that there's a very clear solar cycle dependence that disappears at about the time of maximum. So immediately following our work about a decade ago on doing the magnetic pattern tracking, Dave had the great idea to start looking at tracking the supergranule pattern. And he realized that this actually provided an excellent opportunity to use this pattern tracking technique to probe deeper into the interior. He began by plotting the equatorial rotation rate as a function of depth, as measured by global helioseismology here in the red, and comparing that with the equatorial rotation as a function of wavelength for the supergranules. And he found that there was great agreement. And so this shows that this is a great way to look at the depth dependence of these flows. This suggests that the supergranules are affected by the flows at depths that are equal to their wavelengths, and thus can be used to probe these flows at depth. And this is consistent with the numerical simulations of convection by Stein et al. In 2011. He then began tracking the supergranules in the MDI Doppler images with different time lags. And by comparing the equatorial rotation rate, he was able to calibrate the depth as a function of time lag. So if we look at the differential rotation, he found here, we can see that the supergranule measurements show that the rotation rate increases inward, forming a surface shear layer. The surface shear layer extends to depths of about 50 megameters and to latitudes of at least 70 degrees. Similarly, we can plot the meridional flow. He found a decrease in the meridional flow across the surface shear layer with an equatorial meridional flow at the base of the surface shear layer. This really challenged the fundamental notion of a monocellular meridional circulation and our understanding of the solar dynamo. So much, in fact, that when he tried to originally publish the paper, it was rejected and disputed. I think it took him over a year to get this published. And once he was able to get it published, we started seeing results from helioseismology seeing the same thing. I think Jun Wei was the next one to come out with it, saying that he found this equatorward meridional flow. I want to say that the characterizing the meridional flows in the interior is very challenging. This is because that they are weak, but also because these are not simple static flows, but have variation with solar cycle activity. So there's still a lot of work to be done here. And again, we really need to get a polar mission to really fully capture these flow profiles. We then proceeded to, we've recently tracked the supergranular pattern to create maps of the giant cell convective pattern for the entire HMI time period. These maps can be found, oh, is my video not starting? Okay, there we go. We found, so these maps can be found on our website, solarcyclescience.com. And so these are maps of the giant cell motions, the giant cells themselves moving. In particular, we found that there were two different giant cell regimes. They're the high latitude polar vortices. You can see from the polar view here, these polar vortices spinning around the pole. But at the equator, we find that there's low latitude, we found low latitudinal equatorial Rossby waves. And I don't want to go into it in too much detail, but I just wanted to quickly show the dispersion relationship for these two different regimes. And this is confirmation of the results that Aaron showed earlier by Lotien et al. We see that dispersion relationship for the Rossby waves that are at the low latitudes. At the high latitudes where we have the polar vortices, there's no dispersion relationship. This indicates that these flows are affected just sheerly by the differential rotation and the meridional circulation.
Lisa, a few minutes left.
Okay, thanks. The giant cell differential rotation. So here in the pink, corresponds to the region that would be the Rossby waves. The high latitudes would be where we have the actual, the giant cell polar vortices. In the Rossby wave area, the equatorial Rossby waves are not advected by, but they're actually propagate retrograde relative to the differential rotation. So you see this really flat area. It does not match the differential rotation anywhere. So I'm not so sure if we can use these to really say much about the flows at the low latitudes. Conversely, the polar vortices show a differential rotation rate that matches the internal rotation rate at the base of the convection zone. And so this really is confirmation that we're really probing, using this pattern tracking of these giant cells, we're really actually able to probe down to the depth, the base of the convection zone, down to the tachocline and really capture these flows. And so that brings us to the giant cell meridional circulation. Again, the equatorial Rossby waves shows no meridional flow. It's just very flat here. But we find that the polar vortices are advected poleward, not equatorward. This was really surprising, but I was happy to see the results Junwei showed earlier that showed similar results, but indicating that the direction of the meridional flow at the base of the convection zone in those high latitudes is poleward. So real quickly, my conclusions, pattern tracking can be used to measure the axisymmetric flows throughout the convection zone. Both magnetic pattern tracking and Doppler pattern tracking indicate increase in rotation rate and a decrease in the meridional flow across the surface shear layer with an equatorward meridional flow at the base of the surface shear layer. The differential rotation, we find solar cycle variations in angular momentum with strong shear in solar cycle 24. Meridional circulation shows meridional flow in active latitudes was much more pronounced in cycle 23 than in 24. We find intermittent polar countercells that are currently present at the pole. So I really want to take a deeper look at those. Characterizing the meridional flows in the interior is very challenging because they are weak and not simple static flows, but do have variation with the solar cycle activity. And finally, tracking giant cells at high latitudes shows rotation rates that match the internal differential rotation rate at the base of the convection zone and a poleward meridional circulation. Thanks so much.
Thank you very much, Lisa, for that information-packed talk. Couple of questions in the chat. First one I'll read is from Sushanta. What is the starting latitude of the counter cells? Is the latitude similar for both MDI and HMI?
Yeah, so it's really very hard to really characterize this. And again, this is why I emphasize that we really need to get to the poles. You can kind of see this weakening down to about 70, maybe 60 degrees latitude. This is very noisy. You know, it's really hard to say. And just really, it's very weak. So we're talking, you know, a couple meters per second. And when you're trying to make these measurements at the ecliptic, you know, there's a lot of uncertainty in this. So, but I would say approximately maybe 60 to 70 degrees, but we really need to get to the poles to really nail this down. Great question. Thanks, Dushant.
Yes, thank you very much, Lisa. So we're running a few minutes late. I'm going to close the session, but I'd like to thank all 5 speakers in this session. We had between 100 and 110 and 125 people attending all throughout. There were lots of great talks. It really emphasizes how we need to both observe the poles better and to observe more sunspot activity cycles to better understand how things work.